Okay, welcome to the fourth lecture of Optical Sensors course. In the last lecture, we discussed the basic optics for optical sensing, where we saw that how changing electric field converting to magnetic field and magnetic field giving rise to electric field becomes a wave, and that we saw using Maxwell's equations. We arrived to the wave equation, and from the wave equation we deduced that it is a transverse wave, and its energy, which is given by the Poynting vector, flows in the direction of propagation of the wave. There I pointed out that it is not always true, sometimes it is not exactly aligned with the direction of the propagation of the wave like the wave vector, but most of the times yes, it is true. And there I raised one issue that can we guess anything about the polarization. So, what is meant by the polarization of an electromagnetic wave? So, to understand this, suppose I tie a string to the wall and I am making this kind of vibrations, or this plane, whatever plane. So, the plane of the vibration, like in the plane where the electric field is vibrating, is called the polarization. So, if the electric field vector is changing when it propagates, that will define what kind of polarization does the wave have. Why it is important? It is important because one must understand that when this kind of electromagnetic wave travels through a medium, it interacts with it. The way electric field component oscillates will tell you what will be the outcome of it, and the material when it passes through it, if it has different properties in different directions, then the different polarizations will tend out to give you different results. So, that is why it is very important to understand what kind of thing it is. And then when an electromagnetic wave travels through a medium, it actually interacts with it. So, what happens actually, you can understand it very simply, like you have a molecule and you switch on an electric field. So, the molecule will become polarized, right, it will become like a dipole. This dipole will start oscillating at the same frequency as the frequency of the light which is incident on it, because it is also electric field oscillations, say at a frequency of about 10 to the power 14 per second, and then you have this molecule oscillating almost similar frequency. So, it will become like an oscillating dipole, and this dipole will re-radiate radiation. So, it is called scattering. So, whole of the optics or whole field of electromagnetic research can be divided in two parts. One is a mode problem, where you study that okay, this is a structure, and if you solve for the boundary conditions at this structure, you will find okay, this kind of modes will exist. These are the various ways that light can propagate through it. Or you have a scattering problem. A scattering problem means, suppose you have glass, you shine light on it, what will it make? Microscopically, you will see that its interaction of the molecule in an oscillating electric field. So, there will be an oscillating dipole, and it will oscillate and it will re-radiate light in all the directions, and this radiation from all the dipoles which are getting illuminated will interfere. There will be a superposition of these electric fields, and it will give you the direction of propagation of light in that medium. That is how you do it. So, you will see how scattering affects it, and in later stages we will try to use it for sensing applications. So, for a given K, there are two possible directions of E. So, suppose this k is propagating in this z direction. So, the wave is propagating in z direction. So, E can be either in x plane or y plane. You can see here the blue ones are magnetic field, E is red ones are electric field. So, it is either in y plane or in x plane. Direction of E is called the polarization, direction of E. So, if wave is propagating in z direction, you can have electric field either in x or in y. These two are called independent solutions of the wave equations. And if you make a linear combination of it, you can have a wave say here in this direction. So, you can make another direction. So, it is like this. So, suppose you have x, y, z, and you can have a wave which is traveling in this direction r, then it will have electric field components in all the x, y, z coordinates. You can resolve it in two orthogonal polarizations. We will come to that, and any other configuration will be a combination of these two independent solutions. So, if we see for linear polarization, let us say that the wave is going in plus z direction, and we see from bottom, what will we see? We will see electric and magnetic field vectors. Basically, it is a wave, it is a variation of electric field like this in x direction, magnetic field in y. But what you actually see is like vectors. You do not see this oscillation because it is happening in the same plane. Similarly, the vertical polarized, you do not see any wave. What you see is that this vector, the maximum of the vector you see, you do not see the minimum ones. You see the maximum vector, and that is the electric and magnetic fields. And if you add them together, you find any polarization. You can make any angle from the horizontal and vertical polarized wave like this. So, if a wave is traveling in this direction, it will have orthogonal electric and magnetic fields, but the polarization can be any direction, any angle from x and y. And not only that, we can do more also. How? Take a complex number. So, rather writing E0 as a function, you can write it E0 I E0. What it means here? It means that now it has two components, and they have a phase difference of pi by 2, 90° phase difference. You write the wave equation for a plane wave, and you resolve it in two components, the real part and the imaginary part. Now, take the real part and consider E at the origin, you get to this relation, and E rotates around. So, if I shine a laser from here to you, what you see? You see that the electric field vectors, the direction of propagation of light is in this direction, the electric field vector is oscillating in this plane, but this is not fixed. It keeps on rotating while it propagates, and it forms a circle. So, the tip of the electric field vector forms a circle while it is propagating towards you. So, it can be clockwise, it can be anti-clockwise. So, that is how you define if it is a right circularly polarized light or a left circularly polarized light. But how you define it? Suppose I shine light from me to you, what you see? And for me it is like this circle. Can you see this circle? Yes. So, what you see, this is a anti-clockwise circle, but for me it is a clockwise. So, this is a problem. So, if I shine light, I will say okay, this light is right circularly polarized, but you will say no, it is left circularly polarized. So, this is a problem. So, this is a problem of convention. I mean, it is a matter of bookkeeping. If you use Born and Wolf and Optics by Ghatak and many other books, then you will find that they have considered the observer to be the one who decides if it is a right circularly polarized light or left circularly polarized light. It is not the source of the laser, source of light, it is the observer. But if you use say Jenkins and White, then they are using it other way. So, I mean it is a matter of bookkeeping, but for now let us consider the standard text which we are studying most of the time, Born and Wolf, Ghatak. So, when looking opposite to the direction of propagation, like the direction of propagation, if the light is coming to me, if it is rotating counterclockwise, it is a right circularly polarized, and for LCP it is clockwise. Okay? That is the convention we will consider. Elliptical polarization. So, it is a general solution for a combination of linear and circular polarizations. Elliptical polarization is the most general case. Circular polarization is a special case of elliptical polarization, and similarly linear polarization is also a particular special case of elliptical polarization. So, you see that in linear polarization Ex and Ey are in synchronization. In circular polarization they are 90 degree off phase, but if they are not 90 degree, say they are 80 degree only, what will happen? What will happen if you have Ex and Ey, even if they are 90 degree, but Ex is not equal to Ey. So, you will end up with an ellipse. This will be Ex and Ey, even though they are at 90 degree off phase, they are not equal. So, they will form an ellipse. So, most generally is elliptical polarization, and how you solve for it? You solve for it polarization ellipse. So, suppose I have a random elliptical polarization like this, and if I have a component where I want to measure the how much ellipticity it has, what is the direction of polarization, if it is right circular, right elliptical or left elliptical, then we need to do is that we have x and y axis, and for Ex and Ey we can write these equations. If we consider the axis on the major and minor axis of the ellipse, then it will be like Ea and Eb, and then it will be very simple equation, right. This is the equation of the ellipse. If you have in terms of x and y, you will have this one. So, it is a matter of choice what you choose. So, there are two representations for polarization. This one is used in ellipse symmetry, where you define xi like this, zeta, and you solve for this, or you have this representation where you take tan 2 psi naught is equal to this, you define the ellipticity equal to tan of psi, this angle that comes from b by a. You remember this when it was ellipse. So, it was the minor one is b, major one is a, and you have this ellipse as b by a. So, I will not go into the detail of this. If you are studying an optics course, there you can study it in thoroughly, but here I wanted to give you a glimpse of what this kind of polarizations are. We are more considered about linear polarizations here, because in optical sensing when we come to plasmonics and all these structures, we will be using linear polarizations only. So, if you have elliptical polarizations or circular polarization, delta is equal to plus pi by 2 or minus pi by 2, and you can have psi like this, and A must be equal to B. So, if this is negative right circularly polarized, you have positive, then left circularly polarized, and vice versa, same here. If you have elliptical polarization, you have delta in this range, you calculate Ex by Ey, Ay, and this gives you right or left elliptical polarization. In the other notation, you had psi naught, psi prime and xi, and you see that if this is left circular elliptical polarization and this is right elliptical polarization. For linear polarizations, I leave it to you, you need to solve it. What is a linear polarizer? It transmits one polarization, rejects or absorbs the other. Let us come back to that virtual experiment which I told you, that you tie a rope and I am swinging it like this. What I do is that now I put a chair which has openings like this and I am swinging like this. What will happen? It will not stop the oscillations like this in this plane. So, it is letting it pass through. Now, I rotate the chair. So, now the opening is this way and I want to do the oscillations this way. What will happen? Will it transmit? Answer is no. Why? Because this one is blocking the transmission. So, similarly a polarizer, what is its role? It has lines, one polarization passes through, other one blocks or gets absorbed. So, if the polarization of the incoming light is at an angle, suppose this is my polarizer P and the light which is coming has an polarization at an angle theta, then I can resolve it in two components, say E x and E y, that will be cos theta and sin theta components, and what is coming out is actually E y cos theta, because it is making an angle theta with this. So, if I have my polarizer this way, what is coming out is the cos theta component. So, amplitude is cos theta, E naught cos theta, intensity that is proportional to amplitude square. So, you will get P out is equal to P in cos square theta, or I is equal to I 0 cos square theta. That is called Malus law, law of Malus. So, if theta is equal to 90 degree, what will happen? This term will become equal to 0 for theta is equal to 90 degree. So, there will not be any light. So, if you have a polarizer like this, you have a polarizer like this, where whose path axes are at 90 degree to each other, they are called crossed polarizers, and you do not see any light coming through it. Now, it is like this. So, if you have a set of two polarizers, what is the final intensity? So, if it passes through the first one, so I becomes I naught by 2, you had vertical ones all the directions. What will happen, that you can resolve all the components into cos theta and sin theta terms, cos theta and sin theta terms, and you can add them all. Whatever is coming along this transmission axis, you can add all the components of all the electric field vectors, and what you find out is that it is I 0 by 2, half of them are cut down, half of the intensity passes through. Now, I put this one at theta to this. So, I told you that we get I 2 will be I 1 cos square theta, and if theta is equal to pi by 2, we will get 0. So, that is what we discussed earlier. What will happen if I put a 3? So, now I know that I have one polarizer like this, other polarizer like this, and the result, and so this was y, suppose this is x. So, whatever I was getting was 0, no intensity at all. Now, I put some other polarizer at some angle theta to the first one. What will happen? Adding 2 makes some light pass. So, you can solve for it. You know that after filter 1 it will be E1 y, filter means polarizer, polarizer. After polarizer 2 it will be E1 cos theta, and after polarizer 3 E1 cos theta sin theta, that will be E1 sin 2 theta by 2. So, about 25% intensity after 45 degree. Now, if you put say many polarizers at small angles theta, 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 like gradually changing like this from here to here, what will happen? Total transmission is obtained. So, I leave it to you to prove that. Prove that when many polarizers are inserted between the external crossed ones, so that each with small theta with respect to the other, the total transmission is obtained. What you do is that this one is at small angle say theta 1, and then this one again is making theta 1 with the first one, then theta 1 with the second one, then third one, then fourth one, and now you keep on putting like this, and what you have that there will not be any light lost. If you put only one, there will be about 25%. If you put 2 or 3 or more, you keep on increasing, you will get all the light between these two polarizers. Polarization and scattering. So, in the beginning I was talking about this dipole thing, and I told you that when you have a molecule like this and you have an electric field switched on like this, what will happen, that negative ones will come here, positive ones will go here, and you will form a dipole whose electric field will be in this direction. Dipole will be pointing in that direction, electric field due to dipole will be in this direction. Now, this dipole, since E is equal to E naught e to power I omega t minus kx, you know that there is this omega term, that is the frequency of the electromagnetic wave. So, if this electric field is switching with an with a frequency omega, the dipole will also be switching around a frequency omega. At resonance it will be omega. So, what will happen? It will scatter light. So, suppose I have a dipole here, which has q charges here, q1 and q2, q plus q and minus q, and the distance between them is a, and I want to see that in this solid angle d omega at an angle theta from the dipole, at this solid angle d omega, how much power do I get? So, solid angle means like it is a cone. So, my dipole is vibrating in this direction, and at an angle theta from here I want to see how much light is coming in this cone. So, suppose I have this cone making an angle theta from here, and I want to see how much power is coming through in this cone. So, this is given by this relation dp by d omega is equal to q square, q is the charge, a square, how much is the displacement. If you have a strong electric field, the displacement will be larger. If you have a large electric field, if you have a small electric field, the displacement will be small. So, that is a square, omega frequency of the radiation which is falling on it, the electromagnetic wave, and c is the speed of light, and theta this angle. So, basically it is proportional to sin square theta upon lambda to power 4. What does it mean? It means that if theta is equal to 0, then dp by d omega is equal to 0. That means that the dipole does not radiate along its axis. Dipole is radiating only maximum radiation coming along the perpendicular direction, that is 90 degree. So, polarization dependence, because the induced dipole direction depends on the light polarization. now it comes here. So, I was telling you in the beginning what is the importance of polarization, here it is coming. So, suppose you have a source here and the direction of polarization is like this. So, what it will make it like all the polarizations will be in this direction. So, if all the molecules are polarized in vertical direction, so there will not be any scattering in the vertical direction, all the scattering will be, maximum scattering will be in horizontal direction. So, from the horizontal one you will have maximum scattering, but the vertical ones you will not have any scattering. Now, if I change the direction of polarization to a horizontal, you will get scattered light from vertical both the sides, but not from the horizontal. So, the field distribution in 3 dimension is given by this. So, you can see that in the direction of the oscillation of the dipole you do not have any radiation coming out, all it comes in the maximum, it comes in the horizontal direction 90 degree to it. Sky polarization. So, scattering is perpendicular to induced dipoles and that is to incident polarization. So, if you change the polarization, basically you see different orientation of it and different scattered light. So, this photo was taken with a 20 millimeter wide angle lens with a linear polarizer and sees high degree of linear polarization of the sky 90 degrees away from the sun. You can see here the darker patch. This region is so well defined that the approximate solar altitude can be inferred from the tilt of the dark region of high polarization. So, from the tilt you can see, but you can see that when you have polarized light the way you see objects is different. Why? Because now they are radiating in a certain direction, they are not radiating in all direction. So, you can control how molecules behave when light is incident on it. Okay. Now, we come to transverse electric and transverse magnetic polarization, that is something very important when you study optical configurations. So, suppose we have an electromagnetic wave which is going in an arbitrary direction and the k vector defines the direction of propagation of the wave. The electric field oscillations are like this and the magnetic field oscillations will be in the perpendicular direction. So, it will be like this. Something like this. So, what you see is that if you want to know the electric field and magnetic field in an electromagnetic wave, you have to solve for 6 components Ex, Ey, Ez and Hx, Hy, Hz. So, it becomes very cumbersome to solve the problems of electromagnetism, but what we can do is that we can divide these 6 vectors in a set of 2 orthogonal or you can say independent solutions. So, it will be a set of 2 orthogonal solutions. So, you can make 2 sets actually. Okay. So, let us see how we can do that. So, suppose this is z axis and this is x axis and this is y, and suppose this z axis separates 2 media of refractive index n1 and n2. Okay. So, if a light is incident like this at an angle theta 1, then it will get partially reflected and partially refracted at say angle theta 2, and it will get reflected at the same angle at theta 1. So, this we will prove actually that theta 1, this angle and this angle is equal. But for now let us say that this is the case when light propagating in this direction k 1 get partially refracted to this direction and partially getting reflected. So, it will have the same wave vector. What we see here is that this plane which contains the interface and the plane of the incident ray and the reflected ray, it forms a plane. This is called plane of incidence. So, if your light is such that the electric field component falls in the plane of incidence, while the plane of incidence intersects both the media. So, let us consider the case where electric field component falls in the plane of incidence while the plane of incidence intersects both the media. Then the magnetic field component is perpendicular to this plane. So, you will have E x, for example, for this particular case H y E z. This is called transverse magnetic polarization. Or TM or P polarized. So, what it essentially means that you can have a set of solutions for this configuration where the electric field component lies in the plane of incidence while the plane of incidence sees the change in refractive index, and the magnetic field component is perpendicular to this plane. So, it does not see the change in refractive index. Similarly, one can have another. So, this was the structure, you had y here, you had z and we had x here. So, you can have E y h x h z. So, again the refractive index variation is in x z plane, refractive index variation is in x z plane. So, if the electric field is pointing perpendicular to the interface, this plane, the polarization is called, polarization means actually the set of solution, set of solution. I told you about two independent set of solutions. So, this is called transverse electric or TE polarized, or you can say S polarized. So, you have this configuration where the incident ray, reflected ray, they are in one plane such that this plane intersects this interface, it sees the change in refractive index, then if the electric field is perpendicular in one set of solutions, then it is called transverse electric. So, all we want to find is the transverse direction of the electric field and magnetic field. And what is this transverse direction? This transverse direction is the direction perpendicular to the plane of incidence, subject to the condition that this plane of incidence sees the change in refractive index. So, that is how you define transverse electric or transverse magnetic. Please see that in various cases students make errors when, if I simply switch this axis, suppose I put it x, y and z, and then you remember all this and then suddenly you get confused, and if I changed it say n1 and n2, suppose it is n1 and n2, then what will be TE and TM components. So, people get confused. So, do not just remember, try to understand it. So, if the wave is incident like this and getting transmitted like this, you make a plane of incidence and the component of electric field, if that is perpendicular to it, the electric field perpendicular, then you can have Ez. What are the components remaining? Hx and Hy. This is T. If magnetic field perpendicular, then you have to have Hz, and what is remaining here? Ex, Ey. This is transverse magnetic. So, if I switch the axis or if I switch the interface of the refractive indices, do not get confused. Then there is some other configuration. In this one you see that light was intersecting the interface like this. Now, suppose I have a structure made on glass which has this kind of variation of refractive index. So, suppose this region has refractive index n1, this region has refractive index n2, and this is periodic, and light is incident from the top. So, you have suppose x, y, z like this. So, z is the direction of propagation. You can think like this. Suppose z is pointing down to the plane. So, light is incident on these are actually grating structures. So, suppose you have a grating based sensor, light is falling on it from the top and you want to know the TE and TM response of this structure. How you study this? What will be the polarization of light which will give you the TE response and Tm. So, how you define T and Tm in case of this kind of structure? So, you see that if you remember I told you that when the electric field component is perpendicular direction is in perpendicular direction. So, suppose it is incident normally. So, how you define the plane? It is difficult, right? Plane of incidence. So, if the plane of incidence, suppose if the electric field vector, so what you do is that you take a polarizer, and if the electric field vector lies like this, then it is TE polarized, because the electric field is transverse to the change in refractive index, because the electric field is transverse to the change in refractive index. Electric field of the incident wave is transverse to the change in the refractive index. And suppose you have this kind of polarization. So, it is Tm, because the E field sees the change in refractive index. So, in practical, when you define TE and TM, you are not considering the magnetic fields actually, but what you consider is that if the electric field vector sees the change in refractive index, then the magnetic field will not see the change in refractive index, and then that is why you call it. So, actually TM polarized. So, magnetic field then will be transverse. So, that is how you define TE and TM for different structures. Okay. So, suppose we want to make a sensor and we want to see if it is its transverse electric and transverse magnetic response. It is very important for one to know which way to you put the polarizer. So, you have a sample like this, where the refractive index variation is like this. If the electric field component intersects through, this is transverse magnetic. If the electric field component either falls in the electric field vector either falls in the valley or on the trough, crest or the trough, then it is transverse electric. It does not see any change in the refractive index. So, that is how you find out whether it is transverse electric or transverse magnetic. So, this is kind of a homework for you. Then you have to tell me that what will be the transverse electric and transverse magnetic components for the following configuration. So, in this particular case, you have z axis here, y axis here and x axis here, and in this one is the same and it has different refractive indices. So, n1 and n2. So, that is how you have to find out what is the particular direction. This is something very important which you will be using throughout the course. For example, when we come to plasmonic biosensors, you know that this kind of variations will make different excitations, and this kind of polarizations which is transverse magnetic electric will have different implications. To summarize it, polarization of light plays an important role in direction of propagation and scattering, and it is useful in determining the optical properties of any configuration. So, if you are having a system which is oriented in a particular manner, then you have to choose the polarization in such a way that you obtain the desired optical properties. So, as this course progresses, we will see that different polarizations give different optical results. Thank you.